Okay, I feel like now we're ready to move into the control unit design. So we're on step 4 now. We're going to collect the control points or control signals that we saw we needed, and then we're going to organize them and synchronize them to make control structures. Okay, so the control unit itself, you can imagine, it's got a job, and to do its job, it's going to need hardware, just like the data path had a job and needed hardware to do its job. So we're turning a specification into an implementation. That's what engineers do. We turn specifications into implementations that meet the specifications. So let's start into our control unit design. So we've done this. We're working now here. Together we'll integrate them in the end and have a processor unit. And then we'll move on to chapter 5 for memory. Okay, here we go. Okay, now to add control, again, we're going to be doing design. What we need to do is identify the control points, which is a technical word for the control signals that we already have identified in our data path. If you remember, all those blue things need control. Those are signal names, but we have to figure out when they should be high and when they should be low, what their values should be, and when. So that's what we're talking about here, that we have to do that. So you look at the data path, and you find out, does the instruction fetch unit have some control signals? Does the integer function units have some control signals? Does memory access have some control signals? You find all those control signals, and of course, asserting them and deasserting them at the right times is the job of the control unit. And if you do it correctly, then the operations that you want will be successfully carried out. So you categorize the type of control signals. Flow of data through multiplexers is one thing. Writing state information into clocked registers and memory is a different kind. And then you derive the control signals. Should it be high or should it be low? Should it be 1, 2, 3, 4, whatever? For every combination of bits, you derive what it needs to be, and then you put it all together. And then you implement it in hardware. All right, so let's go to the instruction fetch unit. This is our instruction fetch unit. We talked our way through this. I hope everybody recognizes that the control signals are this one and this one and this one. Those 3 things here. Now, how come the instruction memory doesn't have any control signal? Looks to me like we just give it addresses and out pops instructions. So, yeah, remember, it's acting combinationally. Inputs now determine outputs just a little bit later. We said that. We said that memory that you only read from acts combinationally. Combinational circuits don't, at least this one doesn't need to have any control signals. You might say, oh, the control signals are the addresses. They tell you which data to get out. Oh, Lord, you could say that. But it's not coming from the control unit, so it's not blue. So there aren't any control signals for reading from instruction memory. There aren't any. But there are for controlling this mux, and there are for controlling this mux. This is an adder. It does the same thing all the time. This is an adder. It does the same thing all the time. If something does the same thing all the time, it needs no control. Control means sometimes do this, other times do that. You can see this mux chooses between these two. This mux chooses between these two. Okay, so those 3 signals are our values. And when we want to do an instruction fetch, our branch signal and our 0 signal and our jump signal hold the value of the previous instruction until we change them. Okay, so if we want to fetch the next instruction on fetch, you can see that this value will go here, and this value will go to the memory. Okay. Now for the arithmetic operations, we've got RS and RT are my operands, and I want to put the result into RD. So to put the result into RD, I've got to choose that one on this mux. To get the value of RT through to here, I've got to choose the 0 on this mux. For the operation, it depends, am I ORing or ANDing or shifting or whatever I'm doing. So I'm going to need to do that correctly. It'll go to here, and then you can see on the last mux, I have to choose the upper bus in order to bring it back around to here. And then I'm going to need to write it into here. So the right signal is going to need to be chosen here as well. So that's what we're going to be doing. And if I do any immediates, then I've got an extender that I have to choose. Do I 0 extend or sign extend? And then this mux, if I have immediates, means I have 2 choices here, and I have to have a chooser there. If I write into memory, then the memory write signal will be necessary. If I read from memory, then I don't want to do any memory writing, etc. So for arithmetic, I want to make sure I don't write into here and that I do write into here. I want to make sure that for destination I'm choosing RD. I want to make sure here, I don't care here because I'm not choosing that, but here I do care. I want to make sure I choose that bus and not that bus, so I need a 0. Whatever the op is the one I'm going to choose here. I want to make sure that I'm not branching or jumping because that would change control. All right? And then on the final mux there, I need to make sure I choose the upper bus. So those are the values for all my arithmetic instructions. All of them. Subtract, add, multiply, divide, whatever, and, or, all of them, exclusive or, all have to do that. Now, for adding 4 to the PC, I need to do this blue path. Can everybody see that, I'll add 1 here, I'll go through here. So at this mux, I have to make sure to choose 0. Those have to be set to choose 0. At this mux, I have to choose 0, and then it'll come back in here and write on the next clock signal. For all but branch or jump, that's what I want to do. So therefore, when branch and jump are low, it'll work correctly. Any questions about that slide? So if branch and jump are low, that means I choose the 0 input here and the 0 input here. Because I'm telling the control signal from the mux, choose the 0-ingth bus. Right? That's Turkleese, Jay. 0-ingth. Cipher-ingy and 0th put together. All right. For immediates, it's a slightly different arithmetic set of controls. Because now instead of RS and RT, I'm taking RS and the immediate value. So I need to extend it here. Now if it's an OR immediate, I want 0 extension. If it's add immediate, of course, I want sign extension. I now have to choose the other input of this mux here. Everything else is pretty much the same except that the destination is RT now. So I want to choose the RT for where I write the result to. Remember that? So you'll see that a few things change, but not too many. The main differences would be I care about this now. I want to choose the number 1 bus input here. I want to choose the RT here. And that's pretty much the only changes. Any questions about OR immediate? How would that change if it was add immediate? Only difference would be you sign extend here. And instead of ORing here, you would add here. Only difference for add immediate and OR immediate. Okay, for loading. Now loading's a little different. That means get it out of memory and put it in the register. And you got to compute the memory address. What do we use to compute the memory address? A base register, which is which one? RS. And an offset. Where do we get the offset or the displacement? From the immediate field. What are we going to do with that immediate field? Sign extended. Are we going to multiply it by 4? It's data. It's not an instruction. We're fetching data. We don't multiply by 4. We allow data to be from anywhere we want to get it in memory. So start here with the offset, sign extend it, get it to here to be 32 bits. We're going to add that to the RS value, the base plus the displacement. So we got to choose the right one here to get it here. Got to tell this to add. Now I've created a memory address here. Base plus displacement is my memory address. Where do I send that memory address? Obviously to the address part of my data memory. And a little while later I read out the value. So I want to be sure I'm telling this thing not to write because I'm reading instead. Great, I got it here. How do I get it back into the register file? Well, I got to choose the right input to that mux, which means changing that mux control signal. It comes around here. Where am I going to write it? RD or RT? RT. So I got to make sure that I set this correctly as well. Got it? Control points allow me to choose what I want to do with this data path. What would be a nice traffic analogy to this? What would be a nice traffic analogy to this? If somebody wanted to route a VIP through Ankara's traffic, and they were looking at, a Google Earth view of Ankara's traffic, and they had switches to control the lights, then without all that police stuff, they could make it so the VIP always got green lights and everybody else was red lighted, and you just zip through Ankara, and you wouldn't have to have the police escort, right? So it would be a kind of a global view of how to route through the resources. In the analogy, the resource would be Ankara's traffic. In this case, it's the hardware units in the data path. In the analogy, the switching and the lights that do the control are the control signals here. Got it? Same idea. How do I get what I want from where it is to where it needs to go? And this time, what I want is two parts of an address in immediate and RS to get added together and sent to here, and the output from here to be written back into the register file. That's what a load word does. It reads from data memory and stores that value into register file. Okay, any questions? Yeah,
let's say I'm trying to do some simple arithmetic operation on this circuit, and let's say I will give RS, RT.
It's a simple arithmetic. You give RS and RT, yeah, sure.
And I will get the result 32 bits from the ALU.
Yes, that's right. Whether you added them or ORed them or exclusive ORed them, whatever, yeah.
Then I will use, I think, 0 for the next max, and I will pass the value to the memory. Yeah.
No, not to the memory, to the register file.
Yeah. So in this case, do I read the data from memory?
No, no. An arithmetic operation does not use any data from memory.
That arrow sign represents that the result of ALU goes to data memory.
Look at this. Register operand, memory operand. We don't do this in MIPS. Remember? We don't do it. Yeah.
But in this representation, there is an address comes from the ALU.
Yeah.
So is it executed?
What do you mean, is it executed?
I mean,
if you give an address to a memory and you don't prevent it from reading, it will read and data will be sitting here.
So where is the?
And then we don't choose it. There is no read signal here. There's only a write signal. So every time you put a value here, you'll read from data memory. Okay.
But we don't use it.
But we don't choose it. We don't choose it. See, this is a selector, so we don't choose it.
So don't we waste electricity here?
I hadn't thought of that. Yeah, maybe a little bit. Yeah. Okay, good. Tamam. Okay. Yeah, that's a good point. If we don't need to read and we have the memory chip turned on and active, then it will cause a little bit of power to be spent to activate circuits and change levels. Every time circuits change their value, power is spent. So yes, you're right. There'd be a little bit of power in that. Okay, let's. So there's the load. We just did loading. Now let's go on to the next one, which is store. Okay, to store, as you know, now we want to get a value out of register file and put it into data memory. Which value in register file will be written into data memory? Which value in register file will be written into data memory? Not RS. Store word, RT, displacement, RS. That calculates my address, and then what happens? This goes to there, right? So the RT value is the value we want to write into our data memory. You still need to compute the address. So that means I still need to do the same thing I did this time. Get RS, get the immediate value, sign extend it, choose this to be here, add them together. Now you've got the address. But this time I want to write something and not read something. So what do? I make the write signal high, which says, take this data right here and put it in there. Well, what is this data? It's the RT value, which I'm not going to choose here. Instead, I'm going to choose this one to come through here. Even though they're both blue, you understand this is going to be set to be 1. So we choose this to add to that for the address, and this comes through there to be the data. Any questions about that? So that tells us what the control point values need to be here. Branch and jump are both 0. I don't care. Why don't I care here? Why is this a don't care? Because I'm not writing anything back. See, write is 0, therefore it doesn't matter which one you put here. I'm not going to write anything into here. Okay. This, of course, does matter. It needs to be sign extended. This matters very much. I need to choose this lower one. That needs to be add. This says don't branch or jump, so I sequentially go to the next one. And this must be write. And back over here I have a don't care. Everybody see that? I'm not sending anything through that mux to come back to here, so don't care about that value. So we have 1s and 0s and don't cares, depending on what we want to do with the control signals. I mean with the units we are controlling. So here's the store word. Yeah?
The displacement value.
Right here. That's the base address, which came from RS. And then the displacement value is found, of course, in the immediate field. So I'm taking the immediate field from the operation, sign extending it to be 32, choosing it to be here, and then telling this to add. Yeah. So this, in memory references, this computes my address. My address in MIPS is always two parts: the base register value and the displacement value, and I add them together. Sometimes displacement is 0, but in any case, I have to do this to get the address. Then the address goes to here. Maybe I'm reading, maybe I'm writing, depends if it's store or load. Okay. All right. Now for branch. Okay, for branch, you know that we need to find out if the two registers which we're testing are equal or not equal. So we have to subtract them or do something else like that. So we take the RS and RT values. That means here we have to be sure we choose this one, so that matters. This doesn't matter anymore because we're not doing anything with immediate. We're going to subtract them. And the result is not interesting to us here. What's interesting is the 0 bit, because that's going to tell us what to do here in the control unit. One of these is for jumping. It's still 0. One of these is for branching. It's now 1. That says, okay, maybe we're going to have a change of PC. PC's inside here. The instruction memory is inside here. Remember, a lot of things are inside that. So that's what we need to do here. We're just using a little bit of the data path in order to do a subtraction of two register values. So let's put the control points on. We're not writing anything back here, so that's a don't care. We don't care about this either. Here we do care. Here we subtract. We're not writing anything here, and we don't care here because we're not sending anything back around. All we want is this. This is the result I'm looking for. Is it 0 or not? And once I have that, then I can go into the instruction fetch unit and finish up. So the immediate value here gets sign extended, gets added together with PC plus 1, and it's all about what I do here. These two are going to tell me, take this one, the branch address, or take this one, the next sequential address, All right? So branch sequential devant met All right? There's some more turquoise, Jay. All right, so when branch is 1 on a branch instruction, then it all comes down to the 0 bit. If this is 1, then everything depends on this. If it's 1, we'll take the branch and choose that. If it's 0, we won't take the branch and we'll choose that. Any questions about the controls needed for the branch instruction? Okay. Now let's go to the jump instruction. The jump instruction is a lot simpler. The data path, it hardly does anything at all, because what we're going to do is take the 26-bit pseudo-direct address and send that up to our fetch unit and do the whole decision up there. So there's really not much that happens on the data path. Don't care, don't write, don't care, don't write, don't care, don't write. Basically, don't change anything here, don't change anything here. I don't care what you do with the muxes. Have a look. Don't care, don't care, don't care, don't care. But for Pete's sakes, we do care here. No writing allowed, no writing allowed. What's going to change on a jump instruction? What's going to change on a jump instruction? Program counter. And that's in here. So nothing here changes. No data in register, no data in data memory. Only the PC can change. And so it's not a branch instruction, but it is a jump instruction. So let's zoom in here and see what happens inside our instruction fetch unit. And you know that. Right here's the signal where the jump goes. We're not going to care about this because branch is 0. So already Zaten, we're choosing this one. But the real question is, do we take this one if it's a jump instruction? And we will if jump is equal to 1. So put on the control signals. Yes, jump is 1. So therefore, we take the top branch for loading into the PC. And once we've put that in, that's going to fetch us on the next instruction from somewhere completely different. And that's what a go-to is. It says after this one, the next one is going to be somewhere completely different. Okay? Yeah?
Where does the immediate value come from? Previous circuit?
Where does the...
Immediate 16.
It's not 16. It's the 26 bits target address from the instruction. Yeah, coming from the instruction. So the instruction's got only two parts, the opcode 6 bits and the 26 bits. You send that off to the instruction fetch unit. It's not actually shown here. It should be. Okay, so we have to understand that it's inside here. I mean, the instruction is here, so it's, it's internal feedback. It won't be coming from here, but inside here, we're taking those 26 bits. Now, you can also see that we're sending out from here. Look what we're sending out. RD field, RT field, RS field, immediate field. We're sending out things that the data path needs, but the 26 bits for jumping and the 16 bits for branching just stay inside here. But the 16-bit same field for I-type, which is needed for immediates and for stores and loads, it does come out. It goes to here. Okay? All right. So there's jumping. And so now here's the full picture of our control with the signals that we need to control. 1, 2, 3, 4, 5, 6 for the data path that are single bit, a multi-bit data path, that makes number 7 for the data path, and 2 more for the instruction fetch unit. 9 different control categories, all of which are single bit except this. Since we can do more than 2 things here, that has to be multi-bit. If you want to do 16 operations here, you need 4 bits. Okay? I think on one of the labs for CS-224, you had to design an ALU. It does multi-operations, takes multi-bits to control. Remember that? Yeah, so you know what's inside an ALU because you've designed one. All right, so now let's pull it together in a table. This says 1, 2, 3, 4, 5, 6, 7, 8, and ALU control. 9 different categories here. This is a 3-bit controller. So the 9 categories that I just named, the 9 blue control points or control signals, are listed in the vertical rows, horizontal rows. And then across the top, look at this, are the instructions. When you want to do an add, what do you need to do? You need to do this. When you want to do a subtract, what do you need to do? You need to do this. Or immediate, load word, store word, BEQ, and jump. So here's our 1, 2, 3, 4, 5, 6, 7 instructions. I think I miscounted earlier and said 9. It's 7 instructions. We've got an immediate type, 2 arithmetic types, 2 memory, 1 branch, and 1 jump. Just as vernacular. Obviously, as you build up your instruction set, you can add new columns to this. So what's this information? It's just what we already talked about. What do you see in here? 1s and 0s and don't cares. Yeah. So if you want to do a BEQ, we don't care about that one, we don't care about that one, we don't care about that one. But some of them have to be 1s and 0s, and you're sure that you need to subtract in the ALU, right? But for a jump, we don't even care what we do in the ALU. We don't use it. Lots more don't cares. Just make sure you please don't write anything. Yeah, in those 2. And this is the branch and jump. Okay, for add and subtract, do you notice? Same all the way down the line except for the actual ALU operation. But for OR immediate, it's going to be a little different, isn't it? We need the OR here, that's true, but some of these are different because it's an immediate. So we're not taking 2 register operands. So as you can see here, this data in this table is simply a tabular compilation of all that we talked about in the last slides. Okay, now, let me ask, do you see a truth table? Do you see inputs determining outputs? Okay, what are the inputs when it's an add instruction? These are clearly the outputs. What are the inputs when it's an add instruction? Opcode is 0, but the function code is 32. What are the inputs when it's a BEQ instruction? Opcode is 8. What are the inputs when it's a store word instruction? That's the opcode. Got it? Inputs, outputs. Now, you say, oh, OJ, it doesn't look like the truth tables that you showed us in CS-224. Okay. Well, we can wiggle it around and turn it into a truth table. It's inputs and outputs relationship. All right. So what does that mean if it's a truth table? What does it mean? We can implement with combinational circuitry only, right? We can implement with 2-level combinational circuitry only, right? Yeah, that's what it means. Let's implement. Let's implement, okay? Okay, the first thing is to decode, you have to realize that. For some of these, we have 6 bits of input. For others, we have 12 bits of input. So, and in fact, here we don't care about those, but in general, it becomes a 12 input. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 output problem, okay? So basically, we could imagine that our solution is a combinational circuitry with 12 inputs and 11 outputs. And we know that we can do this in 2 levels real fast if we want to, or we can slow it down and make it a little bit smaller if we want to do a space-time trade-off. But I think all of us would agree that that's probably going to be large in circuitry, and it's certainly going to be complex in specification. I mean, just if you think about trying to make a truth table or a kernel map, that's the number of input combinations, right? Yeah, so 4,096 squares in my kernel map, or 4,096 lines in my truth table. Not so nice. Not so nice. Doable, yeah. Computer algorithms, Varma, of course, but still not so clean and nice. What I'd like to propose to you is a much better design approach, which divides the decoding up into 2 levels: main control and local ALU control. Notice the local ALU control just has to give 3 bits to the ALU. The main control has to give the bits to the rest of the data path. But the main control can take a 6-bit opcode, and if it turns out to be all zeros, then we know that it's an ALU operation, and we can give the other 6 function bits just to here. So this becomes a 6 to n decoding problem, well, plus the ones that go out here. And this becomes an n plus 6 to 3 decoding problem, and everything's much smaller. So we have a definite space gain here. We win on space. Can anybody tell me what we lost on? Time, yeah. How many levels of delay does George Boole tell us that we have now minimum? 4. Yeah, of course. This is a 2-level circuit at best, and this is a 2-level circuit at best. So now we turn 2 levels into 4. So it's slower, but it's quite a bit smaller and quite a bit easier to specify. So the question is that a good trade-off? And the answer will be, it depends if decoding the instructions is on the critical path or not. If slowing that down doesn't hurt the performance of the processor, then we win. If it does, then we lose. So we don't want to do anything to slow down our clock rate, but if this isn't the crucial cause of the clock rate being what it is now, then we can afford to spend that time and gain in space. This is a much simpler problem. So what I'm going to do now is lead through 2-level decoding and show us how it can be done. We're going to watch it go by here the next 15 minutes. It's simply an implementation of what we did in CS-224. So all of you now that took and passed digital design, and that means everybody in the sound of my voice, just watch an example of digital design being done here in the, I want to say, the kind of quick and easy way. So here we go. The 12-input control is going to be very large. To keep the decoder size smaller, we're going to decode some of the lines here and the other 3 here. So what are we saying? Let's go back to the table. So these guys can be determined at the first stage, and these guys will be determined at the second stage. That's essentially what we're saying here. Since only the R-type instructions need the function field bits, let's only give the function field bits when we have an R-type instruction. So then we'll know if it's an R-type or not based upon the value of the opcode. Okay, so now the main control table looks like this. If the op is 0, then I know I have an R-type, and all these are fixed except for this. Remember how I showed you subtract and add are identical except for this? Well, now we've opened it up to any R-type. Want to shift? Want to, well, not, we didn't do shifting in the hardware, but want to OR, want to AND, want to exclusive OR, want to multiply, whatever you want to do. The only thing that changes is this code. Those are all the same. Now, if this is the opcode, it's ORI. If this is the opcode, it's load word. If this is the opcode, it's store word, blah, blah, blah. And we know what to do for those. We have all their control signals for the other 7. Sorry, 1, 2, 3, 4, 5, 6, 7. All the other 8 lines, those are known. And then for the op itself, we know what we want to do in ORI. We want to OR. We know what we want to do in load word and store word. We want to add. We know what we want to do in BEQ. We want to subtract. Right? That's what the ALU has to do for us. And in jump, we don't need any activity from the ALU. It's a don't care. All right, so it's easy to separate. And now does everybody see this is a 6-input to 1, 2, 3, 4, 5, 6, 7, 8 output plus this. 6 to 8 or 6 to 9 or 6 to 10. It's not a big deal. Much smaller decoding in the main control unit. So we shrank it down quite a lot. Okay, now ALU op is the n-bit output from that. Sometimes we know what we want to do. Sometimes we know that we want to add or subtract or, and sometimes we say, we don't know, ask the function code. See, if this is true, we know we want to OR. If this is true, we don't know what we want to do in the ALU. The function code has to tell us. So in fact, the outputs are, I don't know, it's an R type. That's all I know. Please OR, please add, please subtract. That's the things that I need to be able to do. So my outputs need to be able to tell it to OR or add or subtract, or it's an R type. So there's 4 there. This is liberal and gives 3 bits, so 8 things are possibilities in the future. We could add exclusive ORing or ANDing or multiplying or whatever. So there's 3 bits are given, and R type's going to have this code, and these will have those codes. And notice these have the same code because we're asking for the same thing. Doesn't matter for jump. Okay, so now the function field. How will this be decoded? Now we're looking at this here. So if it's an R type, pay attention to this. If it's anything else, ignore that, right? You know, this is irrelevant. If this is an ORI, then this is going to say you should OR. Pay no attention to that. It's useless. Everybody know why we don't pay attention to the function field in an ORI instruction? Why would we ignore the function field in an ORI instruction? Because ORI is OR immediate. What's the format? What's the format? I-type. What do we do with the last 16 bits in I-type? It's the immediate. So are we looking at the last 6 bits and saying, oh, the function field is very important? No, it isn't even the function field. It's part of the immediate. So Bosch, Veritz, chirp. It's not function. If you have an ORI code here, or a load word code here, or a store word code here, or a branch if equal code here, you have an I-type, and this is not what it is. It's a Yalanja function. It's just 6 bits as part of the immediate. Bosch, Ver. But if you have opcode equals 0, you have an R-type, and then this is get-yearly. Got it? So for J-type and I-type, this is get-year-sis. For R-type, this is choke get-yearly. Right? That's the idea behind this. You have to understand that sometimes bits have a name, but they don't really mean that because they're part of a different instruction format. Anyway, so you can see what we want to do here. If it's R-type, this is just the same table we pulled up from the previous one. And so the R-types look like this: RS, RT, RD, function, and op. So the function codes, which are these 6 bits, we're only using and looking at these: add, subtract, and, or, maybe set on less than. So we'll put in a few of them. And you can notice they all begin with 10, so that's useless information for us. Okay? So we really only have these 4 bits that actually give us any meaning from the function field, right? Because this is 6 bits, but we're not using 64 different combinations. So the things we got to be able to do are add, subtract, and, or, and set on less than. That's 5, so we need a 3-bit code going into the ALU. So let's assign these codes here. So I think everybody can see that when I get this, I really only need to look at this, and that says add. If I get this, I really only need to look at this, and that says subtract. So there's my 4-bit input. There's my 3-bit output. So I need a 4 to 3 box, or I take 4 bits of the function code. So now the overall truth table looks like this: the ALU op plus the 4 bits of the function table. Now, when does this matter, these function bits? When does it matter? When do the function bits make a difference to me? Yeah, when I have an R-type. And so the code for R-type is 100. But since I don't have any other codes beginning with 1, all the 100s can become 1XX. So here this means R-type, and that means this matters. This means not R-type, that means this doesn't matter. So these 3 are doing add, subtract, and OR. When do I add? When do I add? Load word, store word. When do I subtract? Branch. When do I OR? OR immediate. When do I add, subtract, and, or set on less than? When it's R-type add, R-type subtract, R-type and, R-type or, and R-type set on less than. Got it? Yeah, okay. And in jump, we don't care about any of this because it's don't care anyway. So we don't even see jump on here. What have I got? 7 inputs, 3 outputs. It's smaller, but a lot of don't cares. So here come the equations now. Okay, so for ALU Control 2, which is this bit right here, I'm going to be saying, when is it true? It's true there, and there, and there. So therefore, I'm interested in this line, and this line, and this line. So I could write equations that look like this. It's true when I have that condition, or I have that condition. Everybody say it's true. Those are the 3 lines that we pulled out. And it's true when I either have this situation, which says that's 0 and that's 1. There we go. Or when I have this situation when that's 1 and that's a don't care, and these are 0, 1, 0. Remember, don't cares go out. So therefore, 1, 2, 3, 4. For 1, 2, 3, 4, that goes out. Or 2, 1, 2, that's all don't care. So these 2 mean that first line. These 4 mean these 2 lines. What is this? What is this? Is this kernel map minimization? Is this computer minimization? What is it? Manual minimization. The engineer is just looking at it and making simple equations directly from the truth tables. Let's go on. ALU control bit 1. Let's go back. Where did it come from? It came from right here. When is this bit set to be true? 1, 2, 3, 4, 5 lines. Let's pull those 5 lines out. They're the only ones that are relevant to us. There they are. Here's the 5 lines. Can you look at that and make some equations for when is it true? It's true when this condition is met or this condition is met. Okay? What's this condition? The first bit has to be low. The second bit has to be low. We don't care about that, and these are all don't care. So that's it. There's the 2 conditions. Notice this says high or low. We said let's make it low, so I have same, same. Don't care about that. So that AND product takes care of those 2 lines. Let's look here. What do I need here? First bit has to be high. That's a don't care. That bit has to be low. That's a don't care. That bit has to be low. So there we go. 1, 2, 3 terms in the second product term. 3 inputs in the second product term. There we go. There's the equation for the second bit. Let's go to the third bit. Back to the table. When is this equal to 1? 1, 2, 3 lines. Let's pull those lines out, put them in a little table and have a look at it. It says it's true when you meet that or meet that or meet that. And guess what? There's no combining here. So the first one says first bit low, second bit high. There you go. This one says high, then low, high, low, high. That takes 5 input AND gate. The third one says high, followed by high, low, high, low. That's also a 5 input AND gate. So 3 product terms summed up together. So there's my equations done by hand. Now, I'm going to just suggest to you, since there's 1, 2, 3, 4, 5, 6, 7 inputs to this, you would probably be struggling quite a lot to get a perfect minimization through kernel maps, because that would be a 7-variable kernel map. Not nice. Well, your choice is, okay, go get yourself a computer program and run the minimization and enter all this data. But you know what? This is pretty clever and pretty quick. A pretty fast way to get the job done. Minimize the bits. So what have we done here? What have we got? We've got the input-output relation for the 7 input, 3 output ALU decoder. We did the stage 2 decoder. We did this, the local control. It turned out to have 7 inputs. We didn't need all 6 of these. 4 was enough, plus the 3 here. So 7 inputs, 3 outputs to do that decoding. So that was done by equation. Now and so this put together there in that thing. Now the main decoder, which is the first block, has to produce what? It has to produce the 3-bit signal that goes to the ALU decoder, and it has to produce all the signals that go to the data path directly. And so those are ALU source, ALU control, the extender operator, the memory write signal, the reg write signal, the reg destination. These are write signals. These go to muxes, etc. So you can eyeball that, and let's have a look at it and see how that's been done. Can anybody look at this and tell me when is ALU source true? When is ALU source true? ORI, or load word, or store word? Can anybody tell me when branch is true? Only on BEQ. Can anybody tell me when reg write is true? R-type, or ORI, or load word? So if we were able to decode that into a signal called R-type, and that into a signal called R-type, and that into a signal called R-type, and OR those 2 together, we'd have a real simple circuit. So I'm going to show you that real simple circuit now. It's done very nicely using a programmable logic array. Look what we got here. If you put up 5, 4, 3, 2, 1, and 0 here and make them all inverted, then we're all low. You're going to get a 1 out of here. Hey, that's R-type. When you put up 5, 4, 3, 2, 1, and 0 into this and you invert those ones, then the code for ORI will turn into a 1 here, and you'll know that this is the ORI signal. Okay, great. So now the reg write, we said when is it true? It's true when you have an R type, or when you have an ORI, or when you have a load word. Programmable AND array followed by programmable OR array. We're done, baby. We're done. That's it. I think that's all there is. Let's see if the next slide shows the whole thing. It may. Yeah, there we are. So now you produce your reg write signal, because there were 3 of those ones, and your ALU source, because there was 3 of those ones. There's only 1 here for mem to reg. It's only true when you have load word. There's only 1 here for memory write. It's only true when you have store word. There's only 1 here for branch. It's true when you have branch. There's only 1 here for... Got it? Piece of cake. Direct. Decode it, then sum them up by looking. Eyeball minimization. Okay? So there's our PLA implementation, programmable logic array, implementing the main control. And a few slides back, we had gates implementing. There we are. How many gates have we had here? How many gates? 3 signals. Therefore, 3 OR gates. How many AND gates? 1, 2, 3, 4, 5, 6, 7 AND gates. 7 AND gates, 3 OR gates to do the local ALU decoding. Come to the big decoder. 6 AND gates and 3 OR gates to do the big decoder. Pretty minimal, actually, to do this processor's control unit. Okay. So now, how would you implement control? We've already suggested that a PLA could be a great possibility. You could also do random logic. Did you notice that we did random logic for the local control and PLA for the main control to give an example of both? They're both possible. In other words, you could split this and do 2 PLAs. You could split this and do 2 gate random logics. You could keep it all together and do a PLA. You could keep it all together and do gate random logic. You know, the dividing isn't the issue. The implementing is either this or this. And now, why would you choose one or the other? What's good about PLA? What's good about random gate logic? Well, the random logic and the PLA have some trade-offs. In terms of design changes, it's true that there's a lot of changes when you're developing something that you need to validate, make this change, try again. You'll be fixing your code a lot this weekend, I'm sure, making changes, running tests. So things change. So in that case, the PLA is easier because it's less work to change it. You just reprogram it, erase it, and reprogram it. And also, when you make changes, the area and timing impact is predictable because it's got a fixed structure. So you didn't change the timing just because you changed some connections on AND and OR gates. The area stays the same as well. In terms of area, there's a trade-off, and it depends on the complexity of the gates. But generally speaking, random logic will have smaller area than PLA. In terms of timing and power, you can almost always get better timing and lower power when you go with random logic. You can tune the individual paths. You have real full control. The PLA's got a cover over it. You can't get inside and change the architecture of the PLA. So this one's a win for PLA. This one's a trade-off, but probably a win for random logic. This one's definitely a win for random logic. Okay? So designing it yourself as opposed to buying a chip and just programming it. Now another approach is to go with a ROM, a read-only memory. Can everybody see that? These are the inputs. These are the outputs. If I call this ROM, then you might call these 12 bits the address, and you might call these 11 bits out the data. So a ROM with a fixed pattern of what's stored at every given address would do this job very nicely. A ROM is a combinational circuit. All right, so that's another possibility. It's also combinational, but its size makes it slow for decoding. Usually it's used sometimes in micro-coded control, but we didn't do that here. We did hardwired control when you have more than one state per instruction. But we're doing a single cycle machine here, which has a single state per instruction, so it's not a good choice. So let's put it all together. Recognize this, there's our data path. Recognize this, there's our instruction fetch unit. Recognize this, that's our control unit now. We've got our control unit in 2 parts. So there's the whole thing, and notice what's red coming out of here is blue in here. So see if I drew a line, control up there, data path here, including the instruction fetch unit. All right? Well, there's the processor for MIPS with 7 instructions. If I was to add JR and JAL, do you think it would change significantly? Probably not too much. If I was to add AND and exclusive OR and add immediate, do you think it would change much? Each. Hardly at all. Okay? If I was to add BNE as well as BEQ, would it change much? Not much. Okay, so there we go. We've got an architecture for our processor, and we've also run out of time. So thank you, ladies and gentlemen, for your good attention. I want you to have a nice weekend, but I want you to study in Chapter 4. Okay, this is good stuff, but you got to put in your share of the time. Thank you.